I'm here to talk about the Go programming language today. The basics is, this is all basically taken from Wikipedia. Go is statically typed and compiled, like Java, Rust, and C. The syntax is sort of similar, is in the C family. So you're going to see curly braces and code that sort of looks like JavaScript, though a little bit different. Go offers a set of neat sort of language features that I'm going to, I'll go more in depth in. But for now, I'm just going to say them out loud. It's memory. It has memory safety and garbage collection, structural typing, and CSP style concurrency. More to come. But I actually wanted to start by situating Go within a family of fairly new programming languages that were developed in the early 2010s during the Obama presidency. If you think about, and if you think about this moment, right, like 2010 or so, it's sort of the height of the ascendancy of scripting languages, Ruby, PHP, Python, other dynamically typed interpreted scripting languages. And there had not been a new sort of like widely used, fast compiled, statically typed language in almost a decade, right? And so when you look at these languages, this family of languages, and I put in Go, Rust, Swift, and Elixir, they all share some common goals, or they mostly share some common goals. To varying degrees, they all aim to operate in the sort of systems programming space of, statically typed, compiled languages while incorporating the convenience of scripting languages. They want programming to be easy and fast like scripting languages, but for programs to offer the efficiency and type safety of compiled languages. So you see like Swift trying to make Objective-C easier, or Elixir trying to make Erlang easier. Because they're some of the first attempts at systems programming in like a long period of time, most of them take a shot at like bringing what they believe to be our new research and important improvements into the world of systems programming to deal with some of the more error-prone aspects of doing systems programming, specifically around memory safety and management. Rust and Go claim to do memory safety better than C and C++, and they often try to make it easier as well. Finally, they are all released sort of at a time when like network computing has just become like a fact of life, and multi-core processors are becoming, just sort of standard in all, in all the chips that ship. So as a result of that, most of them tend to care about having a good story around concurrency. Elixir obviously uses the Erlang virtual machine and concurrency model, which is like a whole ground up rethink. And Rust initially had its own sort of concurrency model based off of some more non-traditional solutions, though they later reverted to like something that's pretty similar to threads, but with a little bit of additional safety. And we'll see that Go has its own concurrency solution that sits somewhere between the like really different model of Elixir and Erlang and the traditional place with like threads that Rust ended up. So yeah, that's the kind of high level overview. One thing that distinguishes Go from those languages is that the people who wrote Go were really concerned with it compiling quickly. But Go was sort of unique in taking one of its like ways we want to emulate dynamic scripting languages to be like, you should be able to write the code and run it almost immediately, and get that sort of like fast feedback loop of like, I wrote the code and now I am getting, and now I get to see the changes. So like, I'm working on this blockchain program, and even running the top level project, which probably incorporates hundreds of thousands of lines of code, it's like 4 or 5 second compile time, for a huge project. So that is, that's a unique kind of like focus of Go, and almost anything that's not that large is going to feel almost instantaneous in terms of compiling. Cool. So that's like my intro. Let's look at what Go actually looks like. Enough of this sort of high-level philosophy. Let's look at some actual Go. This is a little Hello World Plus, but it shows off some important features of Go. Every Go program is made up of packages. It's sort of similar to Java packages, and they start execution at the package main, and then right after. So there's your package declaration. And then right after that, you're going to see import statements to bring in other packages. One thing that is interesting about Go is that this here we're importing format, which is from the standard library. But for anything other than the standard library, packages are going to be imported by a full URL. So you actually need to tell Go where on the internet it can find these packages. Which is pretty interesting. It leads to a bunch, that is actually the basis for a lot of their compilation time optimizations. Go programs are grouped into functions. You can see this is a function declaration. You actually can already see a couple of important aspects of the language. The parameter, this function is a swap function. It takes 2 parameters and they're both strings. So you can see you actually drop the type declaration from the first parameter. It's just assumed that if you don't put a type declaration in front of a parameter, it has the type of the next parameter. It shares the type of the next parameter. And then you can see it actually returns 2 values. This is an important feature of Go, which is it allows you to return 1 or more values from a function. This leads into sort of some other structure with Go, including how it tends to handle errors. And down in the main function, so the main function, sorry, there's no highlight over it. The main function is the function that is going to actually run when you run the program. And you can see that there's one more key feature, and this probably seems like a no-brainer if you're working in JavaScript, but in the world of like type languages, we have essentially some type inference and immediate assignment here, where we're assigning A and B with this colon equal operator, which if any of y'all have ever programmed Pascal, it probably looks similar to that. And basically there, we're just inferring the type of A and B from the return values of the swap function. So that leads to some more terseness that looks a little bit more like scripting. Finally, here we're actually using the format package, and you can see here how we call a function from that package. And there's one hidden feature in here, which is that if you notice the like print line function where it begins with like a capital letter, that actually is super important. As it turns out, basically the way Go decides when you write a package, the way you decide whether somebody who's using your package can see the things you declare or whether they're private to the internals of your package is you just use an uppercase letter. And that applies to both functions and it applies to data types and whatnot. So it's kind of an interesting, it's a very simple way of, sort of just determining visibility. And it works surprisingly well in my opinion. So yeah. Let's look at the type system and dig in a little further. First of all, like you can basically declare a new type with just this type statement. I'm declaring a new type for a time zone. It is an integer value, but it's a different type now than integer. I can't simply assign an integer variable to a time zone variable. I'll need to do a conversion. This turns out to be pretty cool later. Here's some like constant declarations. You don't actually have to put types on constants. They will, the type simply matches the variable you assign it to. So that's another thing that's kind of cool. Here's, Go has essentially 2 collection types. And this is the first of them. It's not actually called an array, it's called a slice. The reason it's not called an array is that Go actually has an array type that you almost never use, because an array type is a collection of a fixed length. You have to declare at compile time how many elements are in an array, which makes it pretty inflexible. And slices, on the other hand, are much more like the arrays you might expect in like a dynamic scripting language like JavaScript. And then we have sorry, by the way, there's one addition. You're noticing there's also here another way you can declare and assign variables. You can put the var keyword in front of them, and then you don't have to assign them right away. You can assign them later with an equal statement. And the single equals is like you can, use it as many times as you want to reassign variables. So, let me, this is the other collection. This is a map. A map is, basically like a hash in Ruby or an object in JavaScript. And here we're actually defining a function type signature. So we're defining a type that is a function signature. And if we implement a function that matches that type signature, it can be assigned to that type. So the add function we implemented here can be assigned to the op type. And then we're going to actually see that used in the final element of Go data types, which is the struct. This is sort of the most complex type that is, essentially allows you to define a data structure with, named variables of different types. Note that the members of the RPC struct here are lowercase, and that actually does matter as well, because again, with the sort of like visibility question, you would be able to access the RPC struct. You would be able to get a member of the RPC, you'd be able to get an RPC struct somewhere in another module, but you could not access the internal variables of those. Those would effectively be private. And here's just a quick assignment to that struct. You can see it's pretty straightforward to assign struct variables once you declare them. Cool. All right, moving on. Yes, so Go is a low-level language, right? As such, like you have to distinguish between things that are values and things that are effectively references, except that they are called pointers in Go, because again, it's a fairly low-level language, even though the pointers are a lot higher level than you might expect in C or Rust. So here is, so you don't declare a reference type, everything is a value, right? Which means that assignment makes a new copy of it, right? So you can see like here I have an X that I made a point out of, that I assigned to a point, and then I assigned Y to X. Now again, because this is a value, if I set X's X member, which is now a public member, to 5, and then I print Y's X member, it's still going to be 3 because it was actually a copy, not a I'm getting the same reference to the same value, right? On the other hand, I can declare a reference to a point, and now if I assign another variable to that reference and I change a member on the struct in the original reference, I'm going to actually get I'm going to find my other reference. If I access that member, it is actually changed. Because again, here we're not copying, we're just assigning. Reference types are, again, somewhat like pointers in that there are reasons to, you can actually allocate them. Here I'm making a string slice that has 10 elements in it. That's me allocating it, though I'm not going to garbage collect it because Go is garbage collected. And I am not going to, I'm not going to garbage collect it. And then there's also like this really weird thing I can do on a slice, because again, slices I'm allocating, this one has a length of 10, but the length can change. And this one here, I'm allocating a slice of length 0, but saying actually make room for 10 elements should I want to append onto that slice without doing a new memory allocation. So that's a pretty low level thing, optimization, to be able to say, hey, I know I'm going to put some elements on it later, so please allocate this memory for me. Again, Go is going to be, is going to have some memory safety. So if I assign the 5th element of my available array where I made 10 elements, where I made it like 10, it's going to be fine. But if I try to assign the 5th element here, even though I allocated the memory, I have set the length to 0, so it is going to produce an out of bounds panic. So that's cool. Let's go on. I think we are, okay, cool. So now we're getting to some of the slightly higher level methods of Go. I'm sorry, the higher level aspects by talking about methods. So Go is like this funny object-oriented language, right? It is object-oriented, but it's really it's a little bit non-traditional in how it does it, right? So let's take our point and our time zone types from before, right? Essentially, here's two methods on the point type, and from the previous slides. And the only way that you make a method is you simply declare a function where in front of the function name you put an additional parameter, which is called the receiver. And the receiver is basically just a function parameter that goes before the function name itself. And by doing that, you effectively get a method. Note that we're using a pointer here with point because we want to actually mutate the values of point inside of this function. And just like a parameter, if you want to modify a function parameter, you need to take a reference. So here we're taking a reference to a point. And then, but then the other thing that's kind of cool is that you can make, you can essentially declare a method for anything. So remember, our time zone is just an integer, right? That's what the value is, but we can still declare like a method on the time zone, and now anything that's a time zone has this method, right? We declare a string, and like you remember, we have like our map of time zones from one of the previous slides. Here, I'm essentially a reverse lookup into the map. Something you might notice here in this method is that this is essentially how we iterate, how we can do iteration in Go with this for structure and the range keyword. Go does not tend to have lots of high-level collection primitives, but you do get a little bit of convenience over like a traditional super low-level for loop where you can range over in this case a map. So yeah, that's it, and this is how you use it. You just, you put it a period right after the variable and you call it like a method, and it feels like a method, right? But it's essentially just syntax. They're mostly a special function parameter, right? Except that there's one more key thing here, yes, which is the last big construct in Go, in sort of Go's like library of structures. And that's this thing called the interface, right? An interface, you might, from the word, you're probably going to think Java interface, and in some respects, it's like that. Let's look at an example. So this is an interface, and an interface is anything that implements a set of method signatures, which is similar to a Java interface. And here's our point struct, which again from the previous slide, sorry. Has an abs method. We define a magnitude interface, and the magnitude interface is anything that has an abs method that returns a float. So here we have our point, and our point implements that method. Let's maybe look at a couple others. Here's two other versions. Here's a three-dimensional point and a polar point. Note that this theta symbol is actually uppercase theta, and that's important because we want it to be exported. So that's kind of odd. In any case, you can see that we've implemented this abs method on all these different data types. And then here we are using it. We declare a point, we declare an instance of the magnitude, we assign the magnitude to X, and you can see that we're setting this mag variable to the result of calling the abs method on this. And you can see that we do this like, we reassign it 2 different times to these other types. We have a polar and a point. And we keep adding these values. Now the key thing you're probably wondering is how do we declare that polar and point 3 all implement the magnitude interface? And the answer is, that you may have already guessed, is that we do not. You do not have to declare that any data type implements an interface. It implements the interface de facto by having the methods, right? And that's actually really I don't know. I feel like interfaces is one thing that Go got really right. You can do a lot of really general things through interfaces. Like, for example, Go has Go's IO library defines a writer interface, and it's simply anything that implements this particular write signature method, right? And so all different kinds of things can implement this write method, and then you can do all kinds of interesting composable things with this by implementing this one interface and then operating on it. By the way, I haven't been watching the yes, yeah. Oh, sorry, Aaron saying basically that yes, interfaces, it's a big thing. You do not have to declare the interface as the type satisfies. You don't have to even declare it in the package and then externally to the package. So I can declare an interface in one package, and if another somebody else implements a data type that has the methods in that interface, that element has that data type de facto implements the interface from another package. So it's kind of cool. Yeah, so I kind of feel like interfaces is something that Go got really well right, and it's a really simple feature, but it works quite well. I want to talk briefly about perhaps Go's most famous missing feature, which is that it has no generics. Go had no generics at launch, and they said it was coming, but it's 10 years later, and there still aren't generics in Go. But it's all right. It is finally coming for real. They've accepted a proposal for generics to the language, and it has a target version, which I believe is 1.18. They're on 1.16, so maybe by the end of this year. But I actually think I kind of wanted to bring up the generics thing, aside from a quick, trolling of no generics in Go, because the whole process around generics, I think, demonstrates one of the kind of like some of the important philosophies in the Go language, right? Go is like really simple, right? They don't want long compile times, and they don't want hard to parse code, right? Even after 10 years, the generics proposal that's going in is like, it's, it does the thing, but it's pretty limited. There's no like fanciness to it. It's not going to be like, you're not going to be writing some like crazy monad, container of a container of a generic type stuff with it. And in fact, like this, in the 20 minutes I've been talking, I've covered most of the language. That's kind of crazy, right? It's not hard to learn Go. It's not hard to read Go for the most part. It is sometimes tedious to program Go because you have a limited set of tools, right? And similarly, along these lines, there's a really simple error handling strategy, which is that there are no exceptions. You just have error return values that you need to explicitly check, and you have the ability to return multiple values from a function. That's like a very simple construct for passing up errors, and the feeling is, well, you should be checking every error rather than just throwing exceptions and hoping they get caught. I think that's an interesting idea. I'm going to talk briefly about Go's concurrency strategy, because I realize I'm actually going longer than I expected at this point. So I'm going to move through this as quickly as possible. So Go has a model for its concurrency. It's this thing called CSP, or communicating sequential processes. It's a system for like coordinating work among independent processes, came up with by a guy named Tony Hoare, I'm not sure, in 1978. Yeah, and mostly Go picked this one because the people who made Go were familiar with it. Just gonna do a brief kind of like intro to what this is conceptually. CSP is all based off of the idea of a process, and a process is just essentially, it defines the smallest, it just references the smallest possible independent unit of work. So I think of like a process in CSP as being like a sprinter. Like you start it, it runs, and it gets to the end. It's just a single sequential series of instructions, and the smallest possible number that you would execute sequentially. Cool. So then, so something that's interesting about CSP is that usually in implementations of CSP, a CSP process is not a full OS process. It's much more lightweight, and it tends to be implemented by the language rather than the operating system itself. Cool. All right. So let's expand the metaphor. You see this metaphor just keeps growing. So you have sprinters. They're like the small processes. So how do you coordinate them, right? So let's imagine a relay race, right? So you have essentially one sprinter has the baton and they're running with it, and the next sprinter waits until they get the baton, and once the baton is handed off, it can run, right? So you have processes, and they're like the sprinters, and they communicate, and they do it sequentially, as in one hands the baton to the other. And the messages they pass back and forth are sequential in the sense that every read, right, every read and write to a message channel can block the process. It's not an asynchronous delivery of messages, which is, if you're in Elixir or Lang background, that might seem unfamiliar. Cool, but it gets more interesting. The interesting difference between a relay race is that processes don't know about other processes. They only know about channels. So you can imagine like the sprinter, they hand off the baton, but they're just putting it into this like little like channel slot, and they don't know who's going to take it out, right? And they just wait and meanwhile the other person is like sitting there, but they're waiting to get something from the baton, and they don't know who's going to deliver it, but they get it and then they run with it, right? Don't worry, it keeps getting more abstract. So another additional element is the process at any point can listen to multiple channels and behave differently depending on which channel produces a message first. So that means like you have like the runner is sitting there waiting for the baton, right? And they'll take a gold baton from one runner or a silver baton from another, whoever shows up first. And if they both show up at once, they just pick a random baton and run with it. So essentially, and then depending on which baton they get, they're going to do different things, okay? So this is now a very like abstract and theoretical relay race, but you basically got CSP as a result of all this. Let's look just briefly at how Go implements CSP concretely. Right, so our goal here is we're going to launch two processes. We're going to have one send a message to a channel, right? Again, the channel is like the way in which the mechanism through which the baton moves, the messages move. And then the other is going to read from the channel, and then they're both going to notify the parent that they're done. So here's our read function. You can see you have, there's an incoming channel. There's one channel to retrieve a value when the write function writes, and the other to indicate that it's done. So you can see you have an incoming channel, and you note this little like arrow notation just says before the word chan means that I'm going to read from it. After the word chan means I'm going to write to it. So here we're going to read our value from the incoming channel. We're going to write it to the screen, and then we're going to indicate to the parent process that we're done by writing to a done channel. Cool. So we have two channels there. Now we're going to look at our write function, and it's pretty similar. Except that this time both of the channels we take in are write channels. And all we're going to do here is we're going to write to our write channel. In this case, we're just going to write the value of bananas, and then we're going to signal that we are done to the parent process by writing to a done channel. And then here is our main function. You can see that we're making two channels here. Again, we have to allocate them, allocate for channels because Go is sort of like low level like that. So we're making the main channel, we're making a done channel. And then we are going to kick off our read and write in parallel. And all we do to do that is we put the word go in front of a function call. By putting the word go in front of a function call, we are creating an independent process that will run in parallel to our main process. So you can think, you have your main function and it's moving. And then when I do go read and go write, that's now two separate processes that are running separate of the main function. And so what's going to happen here is that at some point, the write channel is going to write to this channel here, and then the read channel is going to read from it, and then they're both going to write to the done channel, and you can see here we read twice from the done channel so that we block until both of them have finished, and then we print that we're finished. So what you're going to get out of this is you're going to get bananas followed by finished, and it's a very parallelized implementation of a very simple thing. So yeah, that's the basic idea. There's making channels, reading and writing, reading from the done channel, and that's it. Something that you might notice is that because all of these channels are very synchronous, there's a lot of coordination that happens, right? If you write to the channel, it blocks until somebody reads. If you read from the channel, it blocks until somebody writes. As a result of this, as you can see in the example, the channels, they require a lot of coordination, but they're also on the upside, they're predictable. If what you want is predictable execution, you know exactly when things are going to run. So that's that. Let's look at Go's implementation of choice. So this is that concept from CSP of choice. And here we are going to use Go's construct to implement choice in a case where we're waiting on two parallel blocking operations. Let's imagine we've got essentially we're waiting for user input and we're waiting for a network request to complete, right? And we don't know which is going to finish first, right? So we're going to have two channels, and they're going to represent input coming back from the user or a response coming back from the network, right? So these are our two channels. We have a user input channel and a network response channel. And then we're going to go ahead and kick off our reading of user input and our network request. In this case, this is a demo, so we're not actually going to do either of these. We're just going to make mock versions that wait for a random amount of time and then return a value that we specify, right? So, and then return a value we specify, and then they write to the channel you pass it. Let's see if we, oops, sorry. Did I write? Yeah, so here's my actual implementation. You can see literally all I'm doing is you take your channel, it's going to return a function that you can pass a string to, it's going to wait a random amount of time, and then it's going to write the result into the channel you passed in originally. Cool, so let's do that. And then we are going to actually kick off these two blocking operations. You can see I'm reading the user input. It will eventually read applesauce, and I'm making my network request. It will eventually return some data. And now we are going to wait for both, but we're going to wait for them non-deterministically, right? We're going to wait for them, and what we're doing, you can see here, we have a loop that's running 2 times, and inside of this loop is this structure called a select statement, right? And this is Go's implementation of choice. It looks like a switch, but what it's actually doing is that whichever statement is satisfied first, whether it's the user input channel being readable or the network data channel being readable, that's going to get called, and then we execute the code under that. So no matter which one happens first, we're still going to execute both of them, and then we're going to execute that first, and then we'll wait for the second blocking operation to complete. Cool. So that was a super high-speed intro to all of Go's concurrency. I do want to talk briefly about what it actually means to start Go, to kick off parallel processes in Go. Go defines these. They are defined as a lightweight thread managed by the Go runtime. It's interesting that it uses the word thread. CSP usually talks about isolated processes versus threads which share memory. And actually, in this case, Go does. The goroutines do share memory, which is interesting because that potentially, for those who've done parallel programming, shared memory in parallel programming is kind of a big potential area of error. And interestingly, Go also implements, even though it has this whole model of CSP, it implements if you've done traditional threaded programming, it also implements all of the old threaded sync primitives like mutexes and wait groups, and I guess it doesn't really have a clear semaphore concept, but in any case, all the old primitives for sharing, basically for communicating by sharing data using synchronization primitives are in Go. So if you're familiar with that model in C++, there's a package that implements all of them. And an interesting thing about Go is that the Go docs, though, are very clear. They say, don't communicate by sharing memory, instead share memory by communicating, essentially use channels instead of those old things, except that then they're like, well, you know, but you can maybe go too far with that. So like reference counts are maybe better with a mutex, and also like, you know, I don't know, channels are a better high level primitive, but we know somebody like the low level. Anyway, it's like a lot of it, you know, is like creates a lot. You might be feeling like, well, there's no consistency here, right? And actually, I would say this is my personal view about Go, having written it for a long time, is that like Go does not have a grand unified idea or a like strict ideology or style to how programming should be done, other than it should be simple, right? Java is like, we're going to do highly structured object-oriented programming. Ruby is like, we're going to write this beautiful syntax, really easy terse syntax. And JavaScript is like, we're just going to give you everything because this is the language of the web and everybody's going to want something. And then Elixir, Haskell are like, let's do functional programming, real hardcore functional programming. And Go is just like a simple language with a few key concepts that are fairly disparate and not necessarily like, you know, deeply, you know, integrated with each other. And in fact, like the language creators like advertise that as a feature. They're like, we like orthogonal features because they can be like, you know, worked on independently and like used independently. So I would say that Go values practicality over purity and like small useful ideas over grand design. Another question that comes up a lot is like, what is Go? Like, what exactly is Go? Is it a systems programming language designed to, you know, compete with C? A lot of the people who wrote it say that it is, and in some ways it certainly makes sense. Go does compile to like native code, actual native machine code, not like a virtual machine. And the Go runtime is fairly small. If you compile a Go program, the runtime itself is 2 megabytes. That is still quite a bit larger than C or Rust. And that is because Go is garbage collecting, which is pretty unusual for a systems programming language. You probably would not want to write an operating system in Go because the garbage collection just carries an efficiency price. And also Go's like garbage collector is not actually that great, I think. And then like Go routines themselves have a cost. That's why Rust had a construct very similar to Go routines when it was first created, and then they removed it. So I think the best way to answer what is Go for is to like look at some software written in Go, and you can look at some of the things that you're going to see are pretty big things. Like Docker's written in Go, CockroachDB is written in Go. That's pretty like well liked, robust, kind of scalable database. Most of the blockchain, for better or worse, is written in Go. I don't know if you consider writing blockchain software in a language something that suggests that language is good or suggests it's bad. But it is a fact. Terraform is written in Go. Kubernetes is written in Go. The Kubernetes is written in Go, which is an even cooler version. Anyway, there's just a lot of big production software that's written in Go, which suggests it's practical and it delivers in some fashion. So anyway, that's all I got. I realized that was a super longer than I intended because I was hoping to have more questions, and I think we're actually towards the end of our time. So that's all. But yeah, there you are. Let's bring this back. I'm going to stop sharing because see if everyone's been angry this whole time. Okay, cool.
Thank you, Hannah. That was a tour de force of Golang. You've done a bunch of different languages at this point, in a bunch of different domains, and I'm curious now, like after all the stuff that you were doing with Erlang and Elixir, and you've done all sorts of other concurrent languages as well. Like, do you think that like Go is a language that's suitable for like general purpose sort of web development kind of stuff? Is it more like appropriate for blockchain technology?
No, I mean, like, I'm in the middle. It's so funny. So I left Carbon 5 to go work on fancy blockchain software. Mostly since I've been at Protocol Labs, I've been working on a web server. So you know, we're writing an API in Go. It's pretty straightforward. So I actually think it's probably better for that use case than some of these. I mean, I think it's fine. It's actually good for the blockchain too. I think it's a good way to write. It's basically a good way to write fast programs in a language that's relatively not high barrier to entry in the way that I think honestly Rust is, and like certainly C++ is, and maybe Java would work too for some of the Go use cases, but like the concurrency isn't quite as developed. On the other hand, the other thing I would say about I am not convinced, having worked on Go for 2.5 years, that its concurrency is all that good. I do not, concurrent programming is just kind of hard, I think. So I don't know whether, the fact that it's hard is because Go isn't doing a better job in some fashion, or because concurrent programming is really hard. And it's just like they have it, but like, I don't know, like, yeah, I think that particularly parallelized concurrent programming can be quite tricky, and that, like, it's still tricky to like track your state and like make sure you're not doing weird updates that like overwrite an earlier state and whatnot. I don't know, like, which you can definitely do with like the primitives. It's just that like they don't actually make, I don't know, I don't think they make everything super duper easy or anything. So yeah. Yeah, that's interesting. Mike said that a philosophy is to prioritize people reading Go over writing Go. I think that's true, and it is sort of a good philosophy. The one thing I would say that sucks though is it's so simple that like people write it in tons of different ways. Like sometimes it's definitely got a lot of that like choose your own adventure type of habit with some styles, and so as a result of that, like sometimes reading Go code. Actually, I don't even know if the language is pretty simple, but I think among other things, like the community doesn't have a lot of like very strong, it's not filled with like people who read domain-driven design or anything, like, or solid principles or anything like that. So like, you read a lot of Go code that has like, 75 line functions with, 1-letter variables and stuff, and in fact, like they encourage you to use short variable names, which is fascinating to me. So yeah. Sometimes not so readable, but sometimes readable. Yeah.
I'm glad you called out the toolchain stuff, Hannah. I think that's a thing that like oftentimes gets overlooked when we talk about like comparing languages that we want to apply to a particular problem. Like Go's tools, I think, are pretty good. Like the fast compile times are amazing.
Yeah.
And the formatting tools are amazing. GoFumped is great, and the testing tool with the data race detection and stuff. Those are all rad. So I'm glad you called them out.
Yeah, no, it is, and the other thing is that until you like, I think we work a lot in scripting languages, so we've gotten used to these just sort of like, oh yeah, I read the code and then the thing runs, and we think, oh, the compile time languages are way like faster when you run them, so we should all switch to compile time. You forget when you go back to that a lot of time you lose like 10 seconds while you wait for like your changes to show up, and it can be quite effect on the sort of like ease of your programming cycles. So, and so they've kind of like been really intentional about not letting the compile times creep up there. But the flip side is it means it takes a long time to get them to accept changes, because they're like, well, can we keep the compiler fast? If not, then no. So, yeah, I don't know. It's interesting. It's an interesting language. Yeah, I wouldn't say like I derive a lot of joy from writing Go, but maybe people's joy is not the top priority. And then yeah, and there's certainly aspects of it that are quite there. I think the interfaces are really well done. That was good. I think the total lack of generics, I get that generics have pluses and minuses, but like having to write for loops to like do, to see if a slice has, or an array effectively has like a member in it, like every time for each new type you write, like that's kind of crazy to rewrite the find method over and over again. So, yeah, some of it could be simpler. Other questions? Anyone care?
Anybody?
Yeah. Now I've literally been writing a SQL-based application in Go, and it's not that bad. You have to write SQL because they don't have an active record of equivalent. But also like whether that's a value proposition to not to have an active record equivalent is up for debate.
There's no ORM of any type written in Go.
I mean, there's a SQL ORM. Like, there's like a thing where like you can like plug lots of backgrounds into a thing that you can execute SQL on, but you have to execute SQL, not like execute, you know, a domain language that actually implements SQL. And that becomes, oh, well, maybe there is an ORM. There you have it.
But you guys are inviting daemons,
like,
shows you up.
yeah, I mean, and definitely like having to implement, yeah, we had this application running, you know, SQLite in test and Postgres in production. As it turns out, SQLite does not execute a lot of SQL statements the same as Postgres does in many cases. So, yeah. Oh, the other thing I didn't mention, which I think is fascinating about Go, is that the package system, they now have a package management solution, which is this thing called Go Mod. And essentially all it does is take the dependencies you already have explicitly laid out and like provide various kinds of version locking so you can get the reproducible builds. But beyond that, it's completely decentralized. So there is no like, there's no npm, you know, js.org. Like, disarray, and then like ended up all being fine because it got picked up by GitHub. But like, it's kind of like, it's pretty wild to have like package managed, like centralized package repositories for an entire language, and then like hope the company doesn't go under, you know, which, so I like that aspect of Go, the decentralized thing. So.
What do you recommend for someone who's going to start out with something very low level just to get their feet wet? Just starting with just the docs and jumping on to the Google website.
Yeah, there's a Google website that's like a tour of Go that like is a real simple tutorial that'll teach you the base. I mean, the nice thing about Go is you can learn it pretty quick, right? Because again, it's like not that much, you know, like, so I like the you know, you can use that, and then there's like another site that's like Go by example. And Go is probably a good thing to like, if you haven't done like C or C++ to like do Go before trying to do those, or Rust. Like they're like, it's kind of like somewhere in between where there's a few things that kind of you like need to, that like edge towards pointers and whatnot, but like also like you don't have, you know, pointer arithmetic or, you know, garbage or like manual freeing of memory and all that. That's like, so yeah, I don't know. I would use the tour of Go, and I think there's another site that's Go by example, and then there's like another like best practices site called Effective Go. But the Effective Go is interesting. It's pretty small. It's like, here's some things you should do, you know, like and not like this is the way to write Go, you know. Yeah, I don't. Yeah, it's interesting. I mean, I definitely like I said, I would not. If I were programming purely for fun, I would not use Go. Whether it works as a thing to write code in for professionally, I think is yeah. Anyway, but I guess we're all getting paid to write programming and not doing it for free, so we can't get away. Yeah, Rob.
I've heard things about the size of Go packages being large when they're compiled, and I don't think that's a problem in my opinion. But I'm wondering if that negates the need to like use Docker or like Go programs on different systems.
Not that I know of. I mean, most people I know who run, I mean, you know, people who run deployments often are using, you know, Docker, Kubernetes, all those things. I don't know about the size of Go packages being large. Oh, one thing is that I believe the object format, like they specifically include any code you need, so that like this is part of the fast builds. It is like, if my package A depends on B, depends on C, if like you have an object binary for B, like it specifically does not compile C, like it only, you know, I don't exactly know how it all works, but like there's a way in which you avoid that like super long transitive dependency in the compile. Yeah, but yeah, and also that, yeah, they are statically linked binaries. So like you do not need you know, like there's no separate runtime that you run. It's just like once you compile a program in Go, you can run it from the command line directly. So.
Yeah, I asked that because like a lot of times for when using Docker, you're kind of bundling images that have all these like native dependencies built into the image, but like Go, you don't kind of have that problem. So
yeah,
I sort of assumed like maybe you don't need all that extra.
Well, you still need an operating system, I guess. Well, I guess you could run that directly on a virtual machine. Yeah, I don't know. I don't know why I tend to see people deploy Go in Kubernetes just because that's how they deploy everything now, I think. You know, like it's just sort of like, oh, well, all our other stuff's in Docker, so let's put it in Docker. I mean, Go is certainly Docker friendly in the sense that it's not like, you know, what's it called? Erlang Elixir, where like much of the whole model like depends on certain types of communication that Docker makes pretty tricky. Yeah, I mean, and usually like Go channels are within a program. You can't really do inter-process communication via channels in Go, which is like one of the big selling points of Erlang. So that makes things easier for Docker stuff. Yeah. Yeah, I don't know. It's like kind of a pretty basic standard language. It's not actually that, I don't know, not that innovative in the sense like it does the things, it does it pretty well, does them pretty well. Like, and I mean, you know, definitely, I don't think it has the, like, there's definitely a class of programs that, you know, Rust is definitely the language du jour of writing because it is so performant and so like, you know, it just sort of truly competes with, you know, C and C++ for pure execution. So, but without some of the big downsides of those.
Is there any advantage to use a certain operating system versus another for Go? Or doesn't matter?
No, not that I know. I mean, well, you know, like, well, actually, it is interesting because there are OS specific packages in Go, and like once in a while you'll find something that like is a Go system call that doesn't actually work on like. I found this with like one. I think I was trying to use some weird like version of mmap with Go on Mac, and it turns out there was something that wasn't supported or something. I can't even remember all this, but like, you know, yeah. So there's that element. But for the most part, it's a cross-platform, you know, thing. One other thing about Go is that Go does not really work well, or does not work super well with like FFI interfaces. For those who don't know what FFI is, it's basically a way of like doing like cross-language compiling, usually of like C based code into your regular code. And because of the execution model and the memory safety guarantees, Go does not do super well with that. I mean, you can do it. There's a somewhat sizable cost to it. Like for those of you guys who like do your programming in Ruby, like you may or may not be aware, but the vast majority of the actual like elements of the system that have to be performant are all like C code compiled and linked into your Ruby, which makes your Ruby feel, you know, able to do lots of stuff. But like, you know, the language itself can't implement a lot of the things you would need to do at a lower level to deliver on a, say, a web server. So anyway, yeah, that's what I got.
Cool. Thank you, Hannah. Thanks for your time. And thanks for that cool presentation.
Yeah. Woohoo. Hey.
All right. See you all later.